Okay, so have a look at page 10. Okay, this one is just 16p for 1. You have copper-66 that is a radioactive isotope. When the nucleus of copper-66 decays, the emission includes a beta Pinus particle and a gamma ray photon, right? The count rate produced from a sample of isotope copper-66 is measured using a detector and a counter as illustrated. Now, state 3 reasons why the activity of a sample of copper-66 is not going to be equal to the measured count rate, right? So why is the count rate not equal to your activity? This one has something to do with what I mentioned in the notes before this. I mentioned to you that there's a device that you can use to measure activity. It basically is something called a Geiger-Müller tube, or just shortened as GM tube. So what it does is that it detects radioactive particles. Every time it detects a radioactive particle, it will emit a clicking sound. So the more clicking sound you hear, that means the more radioactive particles are detected. And when you have more radioactive particles detected, that means your radioactive sample is very radioactive. But the thing here that I also mentioned then was that the number of clicks which you hear as count rate, which is actually your count rate, it will never be the same as your activity. Instead, it will always be less than your activity. So one of the things that I mentioned to you is that if let's just say this is your radioactive source, your radioactive particles are emitted in all possible directions. But your device can only detect in one direction. So obviously, you're not going to get a result that's less than actual activity itself. So that is actually the first answer that you have here, where you say that radiation is emitted in all directions, but your detector can actually only cover one direction. This is one possible reason why your why your count rate is less than your activity. It's different, not equal to. Now, and then other possible reasons why your count rate could be different is that you actually have background radiation that's included inside the count rate. Meaning to say, in addition to this radioactive source itself that emits your radioactive particles that is detected by your detector, somewhere around you, there are also other sources of radioactive particles. This is what we call as your background radiation. Okay, so this one could also affect your count rate. It contributes to why it won't be the same as your actual activity itself. And then another thing that you could also probably say is that the radiation itself is absorbed by the air and detector window before reaching the detector. So when your radiative particle is emitted, say for example, your alpha particle is emitted. So when it is emitted, it has to travel through this layer of air, and then it also has to travel through a thin window here before it can reach your detector here. So the thing that could happen is that while your alpha particle is traveling through the air, it gets absorbed by the air. Or if it reaches your thin window, it gets absorbed by your thin window. So your alpha particle actually never reached the detector. So again, this one will contribute to why your why your count rate is going to be different than your activity. Okay, so these are the three most common reasons. There are also some other reasons also. This one could be self-absorption of radiation in your sample. What this means is that your radiation is emitted, but somehow it got absorbed back by your sample. That is what we mean by self-absorption of radiation in the sample. And then after that, you have something called multiple possible counts from each decay. What it means is this. If let's say I have element X, it decays to element Y, you're trying to detect the radiation when element X decays to Y. But the thing is that Y itself may not be stable. This one I know is unstable. Sorry. I know that element X itself is unstable. Then it decays to element Y. But what if Y is also unstable? So if Y is also unstable, by right, it would also decay to another different element. Let's just say Z. Let's just say that Z now is stable. But when it decays to element Z, it also undergoes radiative decay, so it also emits radiation. Okay. So what you're really supposed to detect is supposed to be this only. But then because your element is not yet stable, it actually still continue decay. You actually have some additional radiation which is detected by your counter, which is from this one here. So this one could also account for why your count rate is different from your activity. So this is what we mean by multiple possible counts from each decay. It's actually the same meaning as part D, where they say that the total product is unstable and also emits radiation. Okay, B and D are actually the same thing. Okay. Now, C is actually not so common. Normally, I won't use this. That kind of counter refers to the lag in your counter. That's all. It's not responsive as it should be. That's what we mean by that time of counter. It's not as responsive as it should be. There's some sort of lag. So it's not giving you the true accurate value. Okay, so that is for this one. All right. But I think for your case, you just remember the first three. This one will be good already. And if you want to remember a fourth one, just say that the total product is unstable and also emits radiation. This one will be more than enough already for your partial question. Okay, so this one is all right. Okay, now for part B, you look at part B. In a time of 42 minutes, the count rate from sample copper 66 is found to decrease from this value to this value, from 3.62 to 1.21. Okay, now calculate the half-life of copper 66. Okay, now this one is a bit different. You are not using the decay constant. You're not using this formula yet. Yeah, actually you're still using ln 2 over T half-life. You want to find half-life, but you do not know what is your decay constant yet. Your question here never gave you your decay constant, you see. They want you to find your half-life, but you're still missing your decay constant. You need to find out your decay constant first. The way you can do that is you make use of the information that's given to you. They told you that your count rate decreased from 3.62 times 10 power 4 to 1.21 times 10 power 2. So you can use equation R equals to R naught exponential negative lambda T. The final value is 1.21 times 10 power 2. The initial value is 3.62 times 10 power 4. Then after that is exponential negative lambda 42. Now your 42 is actually in minute. So your decay constant will actually be in terms of per minute. So remember just now I mentioned to you the units need to be consistent. Units must be consistent. So what if one quantity is in one particular unit, the other quantity must be in the same unit also. So here your decay constant you know is going to be 0.1357 per minute. Okay. So now you already found out what is lambda. You can use this equation to find your half-life. But your half-life will also be in minute now, because you see, if your decay constant is in terms of per minute, obviously this one will also be in terms of minute. Okay, this one will be in minute. All right, so use the equation lambda equals to ln 2 over half-life. Sum in the value for lambda. Then after that, solve this equation. Half-life will be 5.11 minutes, just like that. Okay, so this one is fine. Okay, now part C is actually kind of related to what you learned in quantum physics. Quantum physics, you probably will have learned that your atoms have discrete energy levels or something like that. Band theory is no longer inside your syllabus, but you still need to learn about the part where your atoms have discrete energy levels. It relates to your emission spectra and absorption spectra. You learn this in emission spectra and absorption spectra. This one is the one that tells you that atoms have discrete energy levels. What you're seeing here in C is somewhat related to that. To tell you, gamma ray photons emitted from a radioactive nuclei have specific energies dependent on the nucleus emitting the photons. By comparison with emission line spectra suggests what can be deduced about energy levels in nuclei. They are just discrete energy levels in the nuclei. Okay, this is just something that you learn from quantum physics. We haven't covered that. Okay, but I assume you learned it already. So just take the answer as it is. Okay, we haven't gone through this yet, at least not for me. But in your school, you've probably gone through it. So you probably should have an idea of what this means already. Okay, if you have specific energy levels, so if you have specific energy of your photons, it means you have discrete energy levels. That's the main conclusion. All right. Okay, so this one is okay. This one is what page? This one is page 10. Next will be page 12. Let me see what page 12 is. Okay, page 12 is something, again, slightly different. It's no longer on your calculation. Okay, just have a look at page 12. June 16, P42. Okay, explain what is meant by gamma radiation. Gamma radiation, this one is actually isn't written inside your note. What is gamma radiation? But you know that gamma rays in quantum physics, gamma ray is a type of EM radiation, right? Therefore, is a photon. Okay, you sometimes hear that your gamma rays is called gamma ray photons, isn't it? Quantum physics, you already learn what is a photon. It's actually a packet of energy of EM radiation. So what is meant by gamma radiation here? You can actually just say is photons of EM radiation that are emitted from the nuclei. Okay, that's all there is to it. Your nuclei here is actually referring to your unstable nuclei. When it decays, it emits gamma ray photons. It also emits alpha particle. It also emits beta minus particle. But specifically for gamma rays here, you just say it's photon of EM radiations that come out from your nuclei. That's all there is to this question. Okay, now look at part B. The diagram that you see here is kind of similar to the one that you had before. The only difference now is that they have a lead sheet in between. Here, they tell you have a source of gamma radiation that's placed a fixed distance away from the detector and your counter. A sheet of lead of thickness X is placed between the source and the detector. The average count rate corrected for background is recorded. This is repeated for different values of X. The variation in thickness X of ln C is shown in figure 13.2. Okay. So the understanding here is this. When you put a lead sheet here, the lead sheet here is meant to absorb your radioactive particles. It's meant to absorb your radiation. Specifically, it's meant to absorb your radioactive particles. So let's just say you have 3 alpha particles that came out. Because you have something in the way, maybe only 1 alpha particle is able to pass through. Okay, so the purpose of your lead sheet here is to absorb radiation. So this one could also cause your count rate to become even less than it's supposed to lah. But here you're not really explaining why is your count rate lesser than usual. Okay, so your lead sheet here is mainly meant to absorb radiation. It's going to cause your count rate to become less. All right. Now, what if I go and use a thicker lead sheet? If let's just say in my case, the original lead sheet here was a thickness of X. I had 3 alpha particles, only 1 alpha particle managed to pass through. What if I use a thicker lead sheet? If I use a thicker lead sheet, maybe like this thick here, the conclusion you'll probably be able to get is that all the alpha particles are absorbed, none of them pass through. Okay, so the thicker my lead sheet by right, I should have lesser radiation that's able to pass through. Okay, so they've actually tried to investigate this, and then they plotted a graph here, all right, which is actually your count rate in ln versus the lead sheet thickness. So you can see here when your thickness increases, when your thickness increases, your count rate will drop. Your count rate dropping here is indication that more and more radiation has been absorbed. That's why you're getting less than you're supposed to. Okay, so here the absorption of gamma ray in lead may be represented by the equation C0 exponential negative mu x, where C0 is the count rate for x equals to 0 and mu is the linear attenuation absorption coefficient. Use the figure to determine the linear attenuation coefficient mu for this gamma radiation in lead. Okay, this one has nothing much to do with what you learn in notes. It's more on something like general math skill. All right. Okay, so what you have here is a graph of ln versus x. But what they gave you is this. So what you really need to do is that you need to ln both sides of the given equation. If you have C0 exponential negative mu x, you ln both sides, you're going to get ln C equals to negative mu x plus with ln C0. And then here, if you were to equate it to the equation of a straight line, y equals to mx plus c, you can actually work out that gradient is actually negative mu. Okay, negative mu is gradient, or rather mu is negative gradient. So what you want to do is you find the gradient, you find the mu. So before you can do that, your graph actually did not have the lines drawn. They only gave you these points here. So what you're supposed to do is that you're supposed to use a ruler and then draw a line of best fit. Okay, the line of best fit itself actually gives you marks. You see that in your question, there's actually 4 marks given. One of the marks actually come from you showing that your line of best fit is drawn. This is where 1 mark comes from. Okay, so just draw a line of best fit. And then after that, find out the gradient from between 2 points. Ideally, take the points that are at least half a line apart. Okay. So you take the 2 points, you find the gradient, you by right should get some answer that is roughly around here, 0.063 millimeter. Okay. Your range could be different because of the lines that you've drawn. Generally, the marking scheme gave your range as this. Mu is either between 0.057 to 0.065 per millimeter. As long as your answer is between these two values, you're good to go. You will get your 4 marks. Okay. Hey, wait, sorry. This one is for 1 mark. For your 2 marks, the range is actually shorter. It will be between 0.059 to 0.063. Okay, if you have between these two ranges, you will be getting your full marks. Just like that. All right. So 1 mark comes on you recognizing mu is gradient. 2 marks comes on you recognizing 2 marks comes on you getting the correct value. That's all there is to it. Okay, so this one I don't think should be any problem. Okay, now the next one. The value of mu calculated in B is for gamma radiation in lead. You're using the material lead here before this. They're asking you right now, suggest and explain whether the value of mu for aluminium would be same, greater, or smaller. If you change from lead to aluminium, what would happen to the mu? If you change from lead to aluminium. Okay, now your general knowledge would tell you that lead is usually a more absorbing material. This is more absorbing. Aluminium is actually less absorbing. Lead can absorb more radiation compared to aluminium. Aluminium cannot absorb as much. So based on that knowledge, how would you go and deduce that mu is going to be greater, smaller, or the same? Now, just think of it this way. If C is equals to C naught exponential negative mu x, it's the same as C naught exponential mu x itself. Okay, so if you have something that is less absorbing, like aluminium, if it's less absorbing, your count rate is more. This one, you're supposed to be getting more than usual. So if C is more, therefore mu will be less. Okay, that's how you can actually see from the equation itself after knowing that aluminium is less absorbing. So my answer would be something like this. Aluminium is less absorbing than lead, therefore mu is smaller. But as to why is it smaller, you can actually deduce it from the equation that you have right over here. Okay, so this one is for this. Right, so that one is okay. All right, then next possible question. Let me just see what questions left. Okay, next one should be page 12. Sorry, we did page 12. Next one will be page 14. Okay, 14 is that. Okay. Do you want to do one more question or should we just call it one a day? You have to pick up your brother at 5:30, right?
Yeah, I'm not in the rush now. Can finish this question, I guess.
Okay, right. So let's have a look at page 14 then. I'll just finish off page 14 for you.
Okay.
Yeah, okay. Page 14 is November 16 P4141. This one is talking about derivation of your half-life. Sorry, derivation of your equation for half-life, which I mentioned to you last lesson is required in your syllabus. Okay, now radium-222 is a radioactive element found in atmospheric air. The decay constant for radium-222 is 2.1 times 10 power minus 6 per second. Now define what is meant by radioactive half-life. Half-life is just simply the average time taken for number of nuclei to decay to half its original value, or the mean time taken for activity of a sample to decrease to half some initial value. Okay, now regardless of which definition you use, it is advised that you either say average time or mean time. Okay, if you don't write this term, they might deduct your marks because half-life is really talking about the average time. the time is not fixed, sample to sample, but what we can get is an average time out of it. Okay, so that's why we call either average time or mean time. And then you either apply it to number of nuclei or activity. These are the two that will decrease to half its initial value. Okay, so just use the one that you are most familiar and comfortable with, and you should be fine. Okay, so that one is okay. So you erase this one. All right, next one would be show that half-life is related to decay constant by this expression. Now, when you see this equation here, if you go and use your calculator and try to work out what's the value of ln 2, you'll notice it's actually 0.693. So this thing here is actually ln 2. They're actually asking you to derive the equation ln 2 over half-life or some other variation of it. Okay, so you remember what was the derivation? You can either start with number of nuclei or you can either start with activity. In my case here, I started with activity. I know the activity of a radioactive sample will be A equals to A naught exponential negative lambda T. When one half-life has passed, meaning to say when T is equals to T half-life, the activity will be half its original value. So A will be half A naught. My resulting equation would be half A naught equals to A naught exponential negative lambda half-life. Just like that. So from there, what you just need to do is that you ln both sides. So yeah, you ln both sides, but not here. Not yet here. Your A naught will cancel off, giving you half exponential negative lambda T. The next column is where you ln. So you ln half, ln E exponential negative lambda half-life. You're going to get negative lambda 2 equals to negative lambda, negative ln 2 equals to negative lambda T half-life. So lambda half-life is thus 0.693, just like that. Yeah. Okay, so this is your derivation related question. And then the last one is worth 4 marks. So let's go through this one. Okay, now radon 222 is considered to be an unacceptable health hazard when activity is greater than 200 becquerels in 1 meter cube of air. Find out the minimum mass of radon 222 in 1 meter cube of air above which the health hazard becomes unacceptable. Okay, how much mass do you need of radon 222 in order for you to have some sort of health hazard? The thing now is that they tell you when your activity is above 200 becquerels, you would have a health hazard. Okay, so what you can do is that you just find the number of nuclei corresponding to an activity of 200 becquerels in the air. So you use A equals to lambda n, 200 becquerels equals to your decay constant, which you found somewhere. I think it's at the top part of your notes, of your question. Yeah, they already told you your decay constant. It's 2.1 times 10 power minus 6. So decay constant is 2.1 times 10 power minus 6 times n. So n is this value, 9.52, n is 9.524 times 10 power 7. Then after that, you just find your mass again. All right. Mass is number of nuclei times nucleon number times U. This one is the mass of your nucleus. So just multiply all of them together. You're going to get the answer is 3.51 times 10 power minus 17 kg. Just like this. Okay. This is pretty simple work for 4 marks. All right. This is November 17 P41. Question 13. Okay, now they tell you a radiation detector is placed close to a radioactive source. your radiation detector being your Geiger Müller tube. The detector doesn't surround the source. Radiation is emitted in all directions, and as a result, the activity of the source and the measured count rate are different. Suggest two reasons why the activity and count rate may be different. This is similar to what you did one or two questions before this. We actually did this in June 2016 P41. Okay. The question that they are describing here is actually similar to what you're seeing in June 2016 P41. Okay.
Yeah.
This one here, we're asking you that time, why is the activity not the same as your count rate? Sorry, why your count rate is not the same as your activity? So there were a number of reasons. You can actually reuse back
background radiation. Yeah.
Background radiation, emission of radiation, or emission from radioactive daughter products, absorption in air before reaching detector, self-absorption in source window detector may absorb radiation, that time of counter, detector not sensitive to all radiation. Okay. Yeah, but just be mindful of one thing. If let's just say in the previous question before this, we use this particular point, radiation is emitted in all directions, your detector can only cover one direction, you cannot specifically use this point over in your current question because the question already kind of implied the reason already. You see, they tell you radiation is emitted in all directions, right? And then as a result, the activity of the source and measured count rate are different. This one is already given. Okay, they already tell you because radiation is emitted in all directions, that results in your activity and count rate being different. So you cannot use back the same answer that you had over here. Okay, this one was one of the answers before this. You cannot use back this same answer over in this current question because they already put it in the question as the answer. Okay, so just be careful of that now. All right. All right, so this one is already written in, so we can't use that. Okay, now for part B, the variation with time of measured count rate in A is shown in figure 12.1. Okay, this is a graph of count rate versus time. State the feature in figure 12.1 that indicates the random nature of radioactive decay. Now, random nature, we actually went through it a little in the last lesson. That time I mentioned to you that random is just simply where you cannot predict which and when a nucleus will decay because each nucleus has constant probability of decay per unit time. Now, in the form of a graph, how do you know that the process is random? It's mainly because you see that the graph is jagged. Okay, the curve is not the curve is not smooth.
I see.
So it's again, this one tells you the random nature of the radioactive decay. Okay, then the next one will be part 2. Now, part 2, they tell you use figure 12.1 to determine the half-life of radioactive isotope in the source. All right, they want you to determine the half-life, but you see it's worth 4 marks. So surely it is not as simple as just looking at this graph and then just looking at the half-life and then getting the answer, right? You see, because they give you quite a large space and then it's worth 4 marks. So you may be tempted to just read directly the half-life from the graph, but there's actually some things here that you need to do a little. Okay, now, you see, if I talk to you about the graph of count rate versus time, graph of count rate versus time, that looks like this. Now, by right, your graph should actually keep going lower and lower and lower and lower, right? Because this is what we call an asymptote. It will never hit the x-axis, but it will just keep getting smaller and smaller and smaller and smaller still. When you look at this graph here, you will notice that it actually doesn't keep going lower and lower and lower and lower and lower. Instead, it seems to plateau off. It
Yep.
seems to become flat over this region. Okay.
Mhm.
By right, you would have expected it to keep going lower. But
Mhm.
the fact is that it doesn't keep going lower. Instead, it kind of remains almost constant from here onwards. Now, you're supposed to recognize from here that this is actually the background radiation. Okay. There's actually background radiation here, which cause your count rate to remain constant throughout. It doesn't decrease. Okay, because your count rate is now detecting all the, because right now, your sample has already decreased to a very small amount. What you're detecting is actually just the background radiation. Okay.
Okay. Mhm.
So this is your background radiation. When you want to find your half-life, you have to take into account the background radiation. So how you want to find the half-life here is that you have to correct for your background radiation. So I'll just try and illustrate to you a few of the things, the working, try and see whether you can digest it the first time. Now, from the graph, you can see that your background radiation is 10 per minute. Okay.
Mm.
So what you want to do is that you want to take into account the background radiation. All right. Say, for example, you read from your graph, the initial count rate from the graph
Yep.
is 170. Let's just say I read from here. This is 170. Okay. That 170 has the count, the background radiation included inside. If I want the actual one, I need to take 170 minus off it, then giving me 160, right?
Mhm.
Correct? So half of this value after one half-life, this one here is after one half-life, 160 will become 80. If I go through another half-life, 80 will become 40, right?
Mhm.
Now these values that I have, specifically these two values that I have, the 80 and 40, I cannot read this directly from the graph because this graph has background radiation inside. So what I will have to do is that if I want to read from the graph, I will need to plus 10 back. So 80 is 90, 40 is 50. This is the value that I would want to read from the graph. Okay.
Mhm.
So if you read from the graph, if originally you were reading at 170, you will now read at what? 90, and then you read at 50.
Yeah.
Yeah. So these are the times that you have. Yeah. So in my case, if originally I read it at t equals to 0 hours, right now at 90 is 1.6. And then at 50, this is 3.2. This one here, I will notice that my half-life is 1.6. This one is also 1.6. I will try to get the average.
Yeah.
Okay.
Yep.
Right, you're gonna get 1.6. If let's just say in the event this one you got like 1.8, and then this one 1.6, you just take this as 1.8 plus 1.6 divided by 2. Okay. So that is what you want to do here. So that's the reason why your graph, your question here has 4 marks allocated, because they require you to take into account the background radiation, and they require you to do at least twice the half-life calculation. And then if your answer is correct, they will give you the remaining 2 marks.
Right.
Okay, so this one is okay. Then you look at part C. Now they tell you the readings in B were obtained at room temperature. A second sample of this isotope is heated at a temperature of 500 degrees centigrade. The initial count rate at time t equals to 0 is the same as that in B. Okay. The variation at time t of the count rate from the heated source is determined. State with reason the difference, if any, in the half-life and the count rate. Okay. So you're basically trying to repeat the same thing, but this time you heat up the same sample. you heat it up to 500 degrees centigrade, and then you measure the count rate again from time t equals to 0, and assuming that your initial value was the same. Okay, so would there be any difference in the half-life and count rate for any specific time? So in terms of your half-life, we will tell you that your half-life by right won't be changed. It is unchanged because nuclear decay is spontaneous. It's a spontaneous process. It is independent of environmental factors.
Yep.
That one is referring to this part in the notes that time.
Yep, I remember.
Okay.
Mm-hmm.
And then after that, would the measured count rate for any specific time be the same? This one we will say no, because it will be, because nuclear decay is random.
Right.
Because let's just say, for example, if I look back at this one, you see this one is jagged, right? This is all jagged, right? So let's just say, for example, right now, if I were to read this at t equals to 4, right now I'm getting maybe a value of, say, for the sake of our discussion, this one is, say, 36. Okay. At t equals to 4 hours, I'm getting count rate as 36. Okay. If let's just say I have the same sample, and then I take it again at 4 hours, I have another different sample, which I repeat the same experiment again. If I try to read the count rate at 4 hours, chances are it will not be exactly the same as 36. It might be slightly more, maybe this one is 38. If I repeat the experiment again with the same sample, at t equals to 4 hours, my count rate maybe will be slightly lower. Okay, this is what it meant. If let's just say I try to take the count rate at a specific time, maybe say 4 hours, do I expect to see exactly the same count rate? No, you will not see this exact same count rate. It could be slightly more, it could be slightly less. Okay, that is what we mean by random. Okay, the count rate will be different because nuclear decay is random. Sometimes at the same time, you may get slightly more, sometimes you may get slightly less. Okay.
Yep.
If you want to use the definition of random from the notes, you cannot. They just say that the count rate will be different because which nuclei will decay cannot be predicted. But this one somehow doesn't really seem to make sense. I mean, you're trying to relate to why it's jagged. Okay. Okay, so is this one okay?
Yep.
All right, so if this is okay, this one was page 21. Hey, no, this is not page 21. Let me see. This one was page 22. So we go to 24. Maybe I try to find the questions that are a bit difficult for you. You know, we try and do the difficult ones first.
Okay.
32. Because
but this chapter seems a lot easier than the others.
Yes, because the questions you will notice is pretty standard, you see.
Yep.
The questions are pretty standard. I mean, if you've done a few of the examples, you notice the pattern that it keeps repeating itself. And when it does come out, the questions are actually worth close to 8 to 10 marks. It's actually like 1/10 of your paper already.
Right.
So that's why I say nuclear physics is actually something that is very worthwhile to do. Okay, that's why I made it a priority to finish this. So let's just go to a somewhat more difficult question. All right. So 26, let's go to 26. These are the remaining questions that we can do. Okay, so March 2018 P42. This last question here is the one that is a bit difficult. The last part B here. Okay, for the first two parts. This one, I think we can quickly just breeze through this.
Right.
What is meant by radioactivity?
This one is okay. I'm okay.
Okay, this one is okay. Okay, let's have a look at part B.
Yep.
They tell you a small volume of solution containing radioactive isotope sodium-24 has an initial activity of 3.8 times 10 power 4 becquerels. Sodium-24 has a half-life of 15 hours. It will decay to form a stable daughter isotope. So what they're telling you right now is that all the solution is poured into a container of water. After 36 hours, a sample of water of volume 5 centimeter cube is taken from the container and is found to have an activity of 1.2 becquerels. Assuming that the solution of radioactive isotope is distributed uniformly throughout the container of water, calculate the volume of water in the container. Okay, so what this one is trying to tell you is this. Basically, there are a few things to consider. You have two different times. One is at t equals to 0. One is at t equals to 36 hours. So right now, they're telling you that you have the solution pour into a container of water. They want to find the volume of water in the container. So let's just say that this is the original volume, V, having a volume of, say, V, which is what you want to find. Okay.
Yep.
And then after that, they mentioned that they took 5 centimeter cube of water out after 36 hours. So you have a 5 centimeter cube of the same water that you took out, and they found out that it has a becquerel, it's an activity of 1.2 becquerel. Okay.
Yep.
So now the question here that I want to ask you is this 1.2 becquerel going to be the same as, can I also say that at t equals to 36 hours, for this full volume of water, is my activity also going to be 1.2 becquerel? Can I say that? Right now, the question is saying that I took off 5 centimeter cube of water. Inside that 5 centimeter cube, I have this amount of activity. So, if you're talking about the whole full volume of water at the same time, 36 hours, the activity cannot be 1.2 becquerels. Because here, you can just think of it. The number of molecules that I have in 5 centimeter cube definitely would not be the same as the number of molecules in the full volume of water, right? The full volume of the container, right?
Yep.
So the number of molecules aren't even the same in the first place. They cannot have the same activity, right? So you have this problem here right now that you do not know what is the activity, all right? But let's just say you go back to the full volume of water at t equals to 0. Do you know its activity? If you read this question, they tell you that the volume of solution containing sodium-24 has initial activity of 3.8 times 10 power 4. This solution is now poured into a container of water. This one would be your activity for the full volume at t equals to 0.
Okay.
So this one will be 3.8 times 10 power 4 becquerel. Okay. So how would you go and try and do this? Also, I can also try and mention to you that if I have that 5 centimeter cube of water at t equals to 0, at t equals to 0, the 5 centimeter cube, can I say that its activity is 1.2 becquerel? If I just compare between these two, but at different times, would they be the same? Cannot, right?
No, it's not the same. No.
It's not going to be the same, right? So this one is also not something that I know. Okay.
Yep.
So basically, there are actually two different workings here
Mhm.
that you can probably use. So I'll just go through it with you first. We know that activity will always tend to follow this graph here like this. Activity versus time will tend to follow this graph here like this. Okay. A is A naught exponential negative lambda t. Right now, I want to find out the activity at 36 hours for the unknown volume B. I want to find for this one. Okay.
Mhm.
This one here, you see, I can actually, I'm trying to apply A equals to A naught exponential negative lambda t for these two parts here.
Mhm.
Okay. So I know that my initial activity is 3.8 times 10 power 4, then multiply with exponential. Now you see your decay constant, you can actually replace it with just ln 2 over half-life. Right? We know the half-life already.
Yeah.
So we can actually just replace decay constant with ln 2 over half-life. So it's going to be ln 2 divided by 15. So since this one is in hour, this one will have to be hour, so it cancels off. Okay, so here is 36 hours. There's no need for you to change any of the units because hour will cancel off hour. So you just sub that one in. Eventually, you will get the answer as 7,200 becquerels. Okay.
Mhm.
This one is for this. Okay, this one is going to be 7,200 becquerels. For the full volume of water at 36 hours, you're going to have the activity of 7,200 becquerels. But then from here, you actually took off 5 centimeter cube and found out that you have an activity of 1.2 becquerels. So actually from here, you want to use ratio. Okay, this one you want to use ratio. Because I know that 5 centimeter cube gives me 1.2 becquerels. So how many centimeter cube would give me 7,200 becquerels? So you have to use something like ratio. 7,200 over 1.2 times 5 would give me this volume.
Right.
Okay.
Okay. Mhm.
That one is for this. Now, the one in red is also another different type of working, which I can just go through very quickly with you. See, this entire working here was me considering, sorry, this entire work, first part of my working was me considering the full volume first. Okay.
Mhm.
The other way that you can have gone about in doing this, if you just consider the
Minus 5 cm
the
cube.
5 centimeter cube of water,
Mhm.
you this time what you do is that you use A equals to A naught exponential negative lambda t for this one instead.
Okay.
This one you want to find out what is the A naught,
Mhm.
which is basically this. You know the final activity for that same volume is 1.2. You find out what is A naught.
Mhm.
A naught eventually you find out as 6.33336 becquerel. This is the initial activity for 5 centimeter cube at t equals to 0.
Mhm.
Okay.
Okay.
This one would be 6.3336 becquerel. And then from there, you can actually use ratio again. But this time is this one. Let me just circle it out. This one, you will use ratio. If I know that 5 centimeter cube gives me 6.3336 becquerel, how much would give me an activity of 3.8 times 10 power 4 becquerels? That's why you're getting this answer here. It's 3.8 times 10 power 4 divided by 6.236 times 5. Okay. But these two are used, this is used for different times now. This one is t equals to 0. The one before this was t equals to 36 hours. Yeah, this is how it actually became a bit difficult.
I see.
Right. Okay, so this one is okay. Then I move on to some other example. So I'll move on to some other questions.
Okay.
Right. So let's just see what other questions can we do. Okay, let's have a look at 29. Okay, page 29. We're trying to do as much unique questions as possible. Okay. Have a look at page 29. Right, 29, June 2018, P42. This one is going to be the last question. The last part. Okay, so 22, 24. Okay, now 22, 24, 29, 32. Let me just clear off everything. 22, 24. Okay, now we're at page 29. Okay, so this one is June 18, P2, P42. State what is meant by radioactive decay. This one we already know. Just follow the definition in the notes. Unstable nucleus disintegrates into more stable nucleus by spontaneous and random emission of alpha, beta, or gamma radiation while releasing energy. That one is okay. Now just look at part B. We are telling you right now, you have an unstable nuclide P that has decay constant lambda P and decays to form a nuclide D. Nuclide D is unstable and decays with decay constant lambda D to form a stable nuclide S. The decay chain is as illustrated in what you see here. P will become D, D will become S. There are two different decay processes here, each with their own decay constant. So they tell you the symbols P, D, and S are not the nuclide symbols. Initially, a radiative sample contains only nuclide P. The variation with time t of the number of nuclei for each of the three nuclei in the sample is as shown. You have this graph here. Then after that, they ask you on figure 12.2, use the symbols P, D, and S to identify the curve for each of the three nuclides. Okay, so let's just have a look at this one first. How do I know which one is which?
Okay.
If you look at this question here, is it correct to say that nuclide S will only increase with time? Nuclide S is the final product, right?
Yes, it will only, yep.
It will keep increasing with time. Okay,
Right.
so this one, we know that nuclide S will keep increasing with time.
Yep, I understand the question. I understand.
Nuclide P will
continuously decrease.
Okay, will decrease with time. So from here, we know that this line here will definitely be P because it keeps decreasing with time. This line here will definitely be S because it keeps increasing with time. So the other one must be D then.
Yep.
Okay. Right, so that one is okay. Then after that, we ask you, the half-life of nuclide P is 60 minutes. Calculate the decay constant lambda P in per second of the nuclide. So this one, nothing to it. Decay constant is just going to be ln2 over half-life. Change to per second, because we're given in minutes, we need to change to seconds, so times 60. We're going to get the final answer as 1.93 times 10 power minus 4 per second. Okay. Right, so that one is okay. Then after that, part C. The decay chain shown in figure 12.1, lambda p is approximately equals to 5 times of lambda d. The decay change of different nuclei E is illustrated in figure 12.3. Okay, wait. You have what? PDS here. And then after that, they tell you now the decay change lambda p is approximately 5 times lambda d. The decay change of a different nuclei E is shown here. Okay. Right, this one is talking about different nuclei E change to F, change to G with their own respective decay constant. So from here, they tell you decay constant lambda F is very much larger than decay constant lambda E. By reference to half-life of nuclei F, explain why the number of nuclei in nuclei F is the sample is always very small. Okay, so you have to see from here. Because they ask you to, you see, they give you mention or they mention to you decay constant and they want you to relate to half-life. So the first thing that should come to mind is going to be this equation here. Decay constant is not 2 over half-life. All right. Now, if your decay constant is very much larger, what does this actually mean? When your decay constant is large, your half-life will be small. Okay, a large decay constant means a shorter half-life. So if you have a very short half-life, one thing to note here is that your number of nuclei will decrease very rapidly. Let's just say I tell you a decay half-life of say 5 minutes versus a half-life of say 5 years. So if let's just say I have say 100,000 of nuclei A and I also have 100,000 of nuclei B, but they have different half-lives. This one is 5 minutes. This one is 5 years.
Okay.
So you see this one, for this to become half, I only need 5 minutes.
Right.
For this one to become half, I need 5 years. So if I tell you, I give you say 1 hour, I let 1 hour pass, you can see that this one would have decreased a lot of times, right?
Right.
But this one would not have decreased at all, right? So that's the relation here. If you have a very short half-life, given a certain amount of time, it will decrease very rapidly. So here, half-life of F, because the decay constant of F is very much larger, half-life of F is very much shorter than half-life of E. Nuclei F will decay almost as soon as they are produced. Okay, so that is for this.